Okay, so this one here is going to take into account the dilation, and then that's it, right? Okay, so dilation then asks us to actually find lengths. So then when we're done, the hope is that the lengths that we find, when we compare them, we'll see the dilation factor presented eventually. Okay, so the one thing that we need to understand here is it says apply dilation of 2 to AB about point P to create A prime B prime. Okay, so the notation that they use for that, or that you would normally see with that, would be a D with a subscript 2. There's your dilation factor, and then in parentheses they put the pre-image, and then this would be your image. Okay, so that's the notation with that. I mean, dilation of 2 of AB to get A prime B prime. But we're doing this around point P, which is not 0, 0. Okay, so in order to apply the dilation correctly, what we want to do is we remove that point out of the original ordered pairs. So I'm going to actually call this one 3, 1. I'm going to call this one 5, negative 3. If I go 4 minus this one, and then 2 minus that one, it gives me that. If I go 6 minus that one, and then negative 2 minus that one, it'll give me my negative 3. Which makes sense then, because if I go from P to A, I go over 1, 2, 3, up 1, which is that order pair there. If I go from P to B, it's 1, 2, 3, 4, 5, and then down 1, 2, 3. So 5, right, down 3. Now you do the dilation to those. Okay, so the dilation of 3, 1 would go to 6, 2, right? Okay, so I'm going to write A goes from 4, 2, B was at 6, negative 2. They changed to 3, 1, and 5, negative 3. We're now going to dilate those, so now I'm going to multiply those by 2, and they're going to go to 6, 2, they're going to go to 6, 2, and 10, negative 6. Everybody okay with that? And now, so now if I plotted those off of P, so 6, 2 would be 1, 2, 3, 4, 5, 6, and then up 1, 2. So I'd go there. Okay? That's off of P. But from 0, 0, that'd be 7, 3, wouldn't it? So I'm going to add back in. That 1, 1 ordered pair. So this becomes 7, 3. And I'll add back in that 1, 1 ordered pair. So this becomes 11, negative 5. Okay. We should be able to see these. So that's 7, 3. That'd be A prime. And if I go to B prime, 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 1, 2, 3, 4, 5 would be B prime. If we go back through the point, we did that. Okay, go back through A prime through A should go through the point of dilation, and B prime to B should go back through the point of dilation as well. So we've got these two segments, AB and A prime, B prime. So this here is wanting these two ordered pairs. Now it wants these distances. And it says leave answer in simplest radical form. So if we want distances, remember the distance formula is you subtract your x's. So let's look at just A to B. Subtract your x's. I go 4 and 6. Subtract those. What do you get? You get 2 or negative 2, right? But I'm going to square that regardless, so I should get 4. And then I'm going to subtract my y's. So what's 2 minus negative 2? 4, and I'll square that and get 16, right? So the distance from A to B is radical 20. Do the same thing for A prime to B prime. Okay, which would be these ordered pairs now. So if I take 7 and 11, subtract those, you get 4, right? 4 squared is 16. Add to that, then, these two. Okay, so 3 minus negative 5. 3 minus negative 5 gives me 8, right? So it gives me then 8 squared would be 64. So it gives me radical 80. Okay. Now, look at the directions. It says leave in simplest radical form. These are not simplest radical form because I don't see the factor of 2 here that was the dilation factor. What do you say? If I look at these, what do you think the dilation factor would be if you just look at the 20 and the 80? You would think it would be 4, right? Because 20 times 4 will give me 80, right? Or 80 divided by 4 will give me 20. But if I simplify radical 20, what is a perfect square that divides 20? Does 4 divide 20? 4 is the perfect square, right? So what's square root of 4? So 20 breaks down to 2 radical 5, right? Okay, what about 80? 80 is 16 times 5. What's the square root of 16? 4. Okay. Now, if I look at these two and do division on them, what's going to happen with the radical 5s? If I divide those, they're going to cancel, right? So I get 2 to 4 as a ratio. When those are canceled, I get 2 to 4 would be the things left over, right? Is that if I take 2 and apply a scale factor of 2, does it get me to 4? Does that make sense? Okay. If I compare 4 to 2 through division, I get a scale factor of 2. So this one is 2 times as big as that one. Or if I take 2 divided by 4, I get this one is half of that one. So that's what I was trying to get at there, is by getting you to find those distances and divide them, that you do find through, and that's basically what this is. This scale factor of 2 right there is the ratio of corresponding sides. Okay, and that's what I was trying to get us to link between what we're doing now with scale factors or dilation factors and make the comparison to what we've already done with similarity in Chapter 7. Does that kind of make sense? Okay. Make sure I think there's a lot of dynamics going on in that problem. One, obviously, the basic, what do I do to dilate? I need to multiply. But then because it's not around 0, 0, we need to augment the ordered pairs a little bit before we can multiply. Then we need to work that augmentation back out, and then do distance, and then simplify. So there's a lot of dynamics, algebraic and geometric, going on here to be successful in that problem. Not to scare you or worry you, but that's on par with what kind of questions the end of course exam likes to ask. Okay. Does that help? All right. Any others? 19. All right, so AB is the pre-image, A prime, B prime is the image. Determine the point that was used as the center of dilation to go from AB to A prime, B prime. Determine the correct scale factor to go from AB to A prime, B prime. So A prime, B prime is smaller than AB. A couple different ways you could probably do this. We've talked about, and we used it on the last problem, that if I go and draw a line straight through A to A prime, somewhere on that line then should be the dilation point, right? And if I go from B to B prime, somewhere on that line should be the dilation point, all right? What I like to do is understanding, okay, if I'm doing that on those lines, then the key feature of a line is slope, right? So I'm going to try to find the slope between A and A prime. I'm going to go down 1, 2, 3, 4, and over 1. I'm going to repeat that. Down 4, 1, 2, 3, 4, over 1. And if I get enough points by doing that, I can kind of get a good sketch of the line that goes through A and A prime, right? if I go through B to B prime, that's down 1, 2, 3, left 1, 2, 3. So I'm going to go down 1, 2, 3, left 1, 2, 3. And when you know it's that same point, right? So that point right there must be the point of dilation. So if I label it 1, 2, 3, and then down 2. So 3, negative 2. Now, there's a couple different ways of finding your scale factor. Okay. We can look maybe this is the way I would probably do this initially, is I would say, well, this is 0, 0. Okay, if that's my new 0, 0, do it in blue here. Okay, then this point here, remember, subtract the original point out. So this would be 3, so negative 2 minus 1 would give me, actually, how does that work? 3, so I take this point and subtract away that one. So 6 minus 3, and then 1 minus negative 2 would give me 3. And I would do the same thing for B. So I would take 9 minus 3, and that's going to give me 6. And then I would go 4 minus negative 2, and that's going to give me 6, right? Now that this is 0, 0, that's 3, 3, that's 6, 6. I can now compare those two because this one's 0, 0. What do I multiply this one by to get that one? Multiply by 2. Okay. I can do the same thing here with this one. Okay. So that's the way I like to do it, because that's using the technique that we've been working on. But let's look at this. That's down 1 over 4, right? Down 1 over 4. This is down 2 over 8, right? Down 4 over 1. No, I got that backwards. Down 1 over 4 compared to down 2 over 8. Isn't there a times 2 there and a times 2 there? So the dilation factor from AB to A prime B prime, just make sure we understand this. I was going from the smaller one to the bigger one and everything I wrote here, right? But they want you to go from AB to the smaller one. So what is that scale factor actually going to be here? 1/2. Okay? Order matters when we're doing that comparison of similar shapes. And that's what happens. I mean, when we do a dilation, we get similar shapes. A segment is similar to that segment. And when they're one-dimensional shapes like this, I mean, they're always going to be similar. Okay, a segment is always similar to another segment. Does that help? Keep plugging away at that. Like I said, I think it's open till, was it Wednesday? If you have questions tomorrow, we'll talk about those again tomorrow. But I want to move on just because of the test is Tuesday, right? Next Tuesday. Let's talk about probability for a little bit. You guys ever talked about probability? All right, so one thing I want you to understand is probability. When we talk about it in geometry, we talk about it maybe in Algebra 2 class, even when you talk about it in statistics, is a very complex and large branch of mathematics. Okay, we're going to just skim the surface with probability rules and relationships, but you can get into some very, very, very complex ideas and concepts when you're dealing with probability. Okay, You guys see all these curves up here on the board? You guys, have you ever heard of a bell curve before? Okay. The technical word for a bell curve is a normal curve or a normal distribution. That is very heavily inundated with probability, and we use a lot of concepts that we talk about right now to do that type of stuff when you get in the statistics classes. Okay. But I'm just going to try to introduce to you the probability rules that you're going to see on the end of course exam, and then I'd like to show you some probability questions that have come from end of course exams in the past. All right, because they're usually not aligned with how like a textbook asks probability questions. And so we'll get at that maybe towards the end of the week. You guys did ask a couple weeks ago, I think Connor asked us about practice tests. Okay. Did you guys get my email about how to do that? Jagger, you don't check your email, do you? No? Okay. So the Ohio Department of Education provides practice tests. I've sent you an email. It was probably beginning of last week, or if not the week before, with a video link to it of me showing you how to access those practice tests. Okay, and they are just like the actual test. And I think there's released questions. It's not full length tests. There might be around 20 to 30 questions in them, but there's like 5 years worth of released questions. So there's like four or five different tests of anywhere between 20 and 30 questions that you can practice at. Research shows, and research uses probability, but research shows that just by taking a practice test, don't care what you get on it, just by taking it, you do better on the actual thing. Does that make sense? So they've taken people, basically they've done a study and said, okay, well, you're going to take this standardized test. You're going to take this ACT. And they take a control group, which is a group that says you have no treatment. Okay, we're not running you through a class. You're not taking the test a second time or whatever, anything like that. And they will give that control group the ACT for the first time and look at their scores. Okay, they will then take what we call a treatment group. They'll say you're going to take the ACT once, and we're not even going to look at those scores. You're going to take it a second time. Okay, and we're going to compare your scores that second time to the people that took it only the first time in the treatment group. And what they find out is that those people that took it the second time, okay, in that treatment group, do better than the people that did not have that practice test. Does that make sense? All right. And they use probability. That's what we talk about in a stats class, those types of situations. And we analyze whether we get that raw data from those groups, from those situations. And we run through something called hypothesis testing to determine if those scores actually do indicate that there's a better performance on the second or on that treatment group than what we call the placebo group. Does that make sense? Or the control group, I guess. All right. So what I'm saying, if you got some downtime, maybe jumping into those practice tests are good. It also shows you it's because you guys took the English one yesterday. You'll see that the formatting and the platform that you take the test in is exactly the same as the air test. Okay. So talking about probability, and we're going to jump around. Chapter 13 is all about probability, but there's some sections in here that we'll skip for the time being. But in probability, these terms are very important. Okay. The word outcome is the possible result of a situation or experiment. It's the things that could happen. Okay, so when I ask you, if I flip a coin, the things that could happen are heads and tails, right? So heads and tails are referred to as outcomes. Okay, if I roll a dice, the numbers 1, 2, 3, 4, 5, 6 could happen. So 1, 2, 3, 4, 5, 6. Each of those are referred to as an outcome. Okay. An event is a single outcome or group of outcomes. Okay. So that would be, and this is where we see events notation-wise, most often, if I say, let's just go to flip a coin. If I say the probability of getting a tails, what we do is we say capital P for probability, and we put in parentheses here, tails. Tails, it is an option, it's an outcome, but because I'm worried about that specific outcome, we call it an event. Okay? It's basically narrowing our focus on, if we know our outcomes are heads and tails, and we want to know what's tails, well, that's the event then, out of those outcomes. It's a group of outcomes. If I look at rolling the dice, and I want to know what's the probability of getting an odd number, okay, then rolling a 1, a 3, or a 5, that's a group of outcomes, so that is our event. Okay, does that make sense? Okay, the event is always going to be in the parenthesis here, all right, and that then is going to be a group or an item out of an individual group or individual item out of your outcomes. Favorable outcome, that's the outcome that is desired. Okay, favorable outcome is the outcome that is desired. Maybe it's the outcome of interest. So maybe if we have everybody in this class and I ask, what's the probability that I randomly choose somebody? So I close my eyes and I just pick a name out of a hat. What's the probability that they are left-handed? Okay, left-handed would be the event. Does that make sense? Okay, the outcomes would be left-handed or right-handed, correct? Okay, and then the favorable outcomes, let's say that there are 3 of you in here that are left-handed. So favorable outcomes, the outcome that is desired, there would be a value of 3 attached to that. Does that make sense? Okay. Sample space would be the set of all possible outcomes. So sample space, I think there's 15 of us in here on a normal day. Okay, so 15 would be that sample space. So we'd have 3 left-handed people out of 15. That would be our probability then, 3 out of 15. So sample space is the set of all possible outcomes. What is different? This is what you analyze in a stats class. Because every stats class, a lot of times, like if we go into like a textbook that's just called like elementary statistics. Okay, that's what the textbook we use for my college class here is. And you start looking through it, the 3rd chapter usually, sometimes the 2nd chapter of every stats textbook is dedicated solely, there's usually about 2 chapters that dedicate solely to probability. That's all you talk about, okay? Because you need an understanding of probability to do this type of thing, okay, that I've shown you on the board back here with these curves. What is difficult a lot of times when we get into dealing with probability is recognizing what is the sample space, okay? So we'll discuss that as we move forward, and that's usually the one thing that as I do problems with you, that's the first thing I'm going to try to focus on, because if my sample space is messed up or incorrect, there's absolutely no way that I'm going to be able to get the right answer. Okay, so we have to target that first. This is referred to as classic probability. Okay, classic probability says if the outcomes in a sample space are equally likely to occur. Okay, what that means is that if I am going to put your names in a hat, okay, and I'm going to close my eyes and reach into that hat, then I have the same chance of picking Jagger's name as I do picking Brady's name. Does that make sense? Okay. We want to make sure that events are equally likely to occur. Okay. And the idea of that, maybe we think about it this way: if I were to put your names in a hat, let's put them all on index cards, but then I put one of your names on like a full-size sheet of paper, like an 8.5 by 11 sheet of paper, does that one now have maybe unequal chance of being selected? That makes sense? Okay. So, and somehow I've structured it to where somebody, there's some, we call it bias. So there's some bias that's occurring in choosing an object, and that's gonna skew our probability. It's gonna mess our probabilities up. So if the outcomes of a sample space are equally likely to occur, the probability of an event, okay, you see here that we notate that with P, capital P, and then the event, whatever it may be, and usually we describe it with words. Okay, there will be times where we describe it with just numbers and maybe inequalities and that kind of stuff, but that won't be for a while. And that probability is a numerical value from 0 to 1 that measures the likelihood of an event occurring. Okay? We're not saying that that is going to happen. We're saying it's the likelihood. Does that make sense? Okay? So what we have is the probability of an event is the number of favorable outcomes, the number of outcomes that are aligned with the event, okay, divided by the number of possible outcomes. Okay? And here's a scale that shows you, based on our probability, of what is going to happen. Okay? So if we're at 50 or 0.5, okay, that means that it's equally likely to occur or not occur. So if I say I'm going to flip a coin, and I say it's going to land heads, it's 50% chance that that's going to occur, right? Okay, 50% chance that's not going to occur. Okay, so they're equally likely events to occur. If they say today has a 50% chance of rain, okay, that's pretty much saying it's going to rain or not going to rain. It's 50-50, right? Okay. Now, if they say if it's going to be a 98% chance of rain, then we can be almost guaranteed that it's going to rain, right? Does that make sense? Okay. If I tell you I'm going to flip a coin and a side is going to show up, a heads or a tails, that's going to happen, right? I'm not going to be able to flip a coin and it rest on an edge. Like a face is going to show up, okay, or a side of that coin is going to show up. That would be 100%, and we say at 100% is certain to happen. Okay? Does that make sense? If we get 0, so let's say I flip a coin and I say, well, what's the probability that a giraffe shows up? That's not going to happen, right? Just pretty bizarre. Okay? So that would be impossible. Okay? So, and on our scale from probability 0 to 1, okay, 0 being impossible or not going to happen, and 1 being certain it is going to happen. Okay, these are decimals. We change them to percentages. Be 0%, 50%, 100%, just by moving our decimal place. Okay, so there are two types of probability that we are going to investigate. Okay, so that I say that's classical probability. That's kind of the overarching concept that all of probability kind of branches out from. Okay, we have something called experimental probability. Experimental probability is the idea that we are actually conducting an experiment. We are actually going through a procedure. Okay, we are actually going through a procedure. It is based on the actual results of that experiment. So if I were to take a coin, okay, and I flip that coin, okay, and I flip it 4 times, how many heads show up or how many tails show up is not going to be 2 and 2. Does that make sense? Okay. You might be a person who flips a coin 4 times, and you might get 4 heads, 0 tails. You might get 3 heads and 1 tail. Okay. You might get 1 head and 3 tails. You might get 2 and 2. Okay, but what you get is experimental. Okay. So I'll show you guys here. Let's see if I've got the ability to give this to you real quick. We're going off of. We should be good. All right, so what I'm able to do here is you can see that when I recalculate this, it changes the heads and tails, right? So all I want to do real quick, I'm going to take this and I'm going to drag it down to 10, which is the idea that I've flipped the coin 10 times. Okay? So right here, what I'm going to do is I'm going to say count if, and I'm going to say this says heads, and then say count if things in this column say tails. Okay? And I'm going to say count if this column has something in it. Oh, that's not right. How do I do that? Don't worry about it. We'll just do this. All right, so we can see here that if I flip a coin 10 times, we think maybe we should get 5 and 5, right? But experimentally, it shows that I get 7 and 3. 7 heads, 3 tails. Okay? If I do it again, let's say, go down to, let's roll this through 20. Now I get 12 and 8. Okay? If I go through 50, so 12 and 8 is obviously not 50-50, right? 24 and 26. That's better. That's closer to 50-50, right? What we find out, and it's going to take a minute for me to scroll all the way down here, but the more you do an experiment, and this is what we learn about in a stats class specifically, the more I do an experiment, the more reliable my results are. Okay? Meaning that if I want to figure out if there is an issue with, well, let's say that I've manufactured a new treatment for cancer, and I give that treatment to one person and they get better. If you're person number 2 that I'm going to prescribe this new medication to you, are you real confident that it's going to work for you? No. Okay? Think about the vaccines that everybody's getting right now. Okay? Now, we've done a lot of studies and tests on those vaccines, but they're not long-term tests. Okay? So, are we real confident that they're going to do what they say they're going to do? Are we real confident that there's not going to be any side effects later on down the road, 5 years, 10 years from now? We don't know those things, okay? But the more studies that we do, the more people that get the shot, and then we track them and follow up with things that happen to them later on in life, we can start to get an idea that that vaccine was beneficial or was not. So the more testing and experimenting that we do, the more our results are going to align with what they should align with, what reality says they should be. Okay, so I'll go down to 3,000 here, okay, which is nowhere near enough. Okay, but if I look at those, and I could say, take C1 and divide it by 3,000, and take C2 and divide it by 3,000. Is that pretty close to 50-50? Yeah, okay. But if I took, remember we had 12 and 8? If I take 12 divided by 20 and 8 divided by 20, you see that those are further off from being 50-50, right? Because 20 is a small sample space. But if I have 3,000, that sample space is much greater. Okay, so we call that the law of large numbers, which means the more that you do an experiment, okay, the probability starts to match up with what we call theoretical probability. Theoretical is probabilities based on what we expect to happen. I expect when I flip a coin to get heads 50% of the time and tails 50% of the time, right? Okay, we know experimentally, just through what we just did with Excel, that might not happen. Okay, what we learn though, that in the long run, as we do the experiment over and over and over and over again, Okay, and I didn't do it nearly enough. But what we find out is that experimental probability eventually equates to theoretical probability. So the idea then is if I've got a vaccine or I got this new cancer treatment or whatever, if I give it to enough people, okay, and record the results of those individual trials, okay, I can then start to have a better idea of what that would do for an entire population. Does that make sense? Over the long run, okay? So we've had the flu vaccine for decades, right? And it's got about a 60% efficiency rate, okay, or effectiveness rate, okay? And we know that because we've been giving it for decades and keeping track of that data of people have gotten the flu, that kind of thing. And we can say, okay, we know that it's going to be 60% effective no matter what population we give it to, okay? So 6 out of 10 people get the shot, they're not going to get the flu, okay? But that's the difference between something we call experimental probability and something we call theoretical probability, okay? So businesses use these two things together in tandem to make decisions. Here it says a quality control inspector samples 500 LCD monitors and finds defects in 3 of them, okay? So what they'll do, P&G does this we got a lot of manufacturing businesses here in the area. P&G, we got Dana, we got Ford, Pepsi. They all have a group that does it, a quality control group that takes samples off of their line of manufacturing and tests them, okay? So this one is LCD monitors. Now, they don't have the time and resources to take every LCD monitor that they make and run it through a test to make sure it's working. Does that make sense? So what they do, maybe they make a million LCD monitors in a month. Okay, there's no way they can test all 1 million. They don't have enough people to do it, enough time to do it. So they will what we call systematically sample. Okay, they will say we're going to take the maybe the 100th LCD monitor that gets made, and then we'll take the 200th one that gets made, and then we'll take the 300th one that gets made, take the 400th one. Does it make sense? They they space them out, and then they grab that one off of the assembly line, and then they test that. So what they've done this so that they've created a sample of 500, okay, and they find out that there's 3 of them that are defects, okay. So it says, what is the experimental probability that a monitor selected at random will have a defect? Well, the probability of a defect would be the number of outcomes that are aligned with our event. There were 3 outcomes that were defects out of the total sample space, which would be 500. Okay, so 3 divided by 500, okay, is going to be our probability. 3 divided by 500. Now, think about this. If I make a million LCD screens, so 3 out of 500 is kind of the experimental, right? Okay, but we've got a pretty large sample space there, which would mean that probably when I go to 1,000, there's probably only going to maybe be 6 monitors, give or take a few. Okay, might be 5, might be 6, might be 7, might be 8. Okay, but it's going to be around 6 that are going to be defective. Does that make sense? Okay, so if we can do this experimental probability scenario and say 3 out of 500 are going to be a defect, then if I have 15,240 that are made in a month, how many of those are going to be a defect? Well, I take the probability that out of 500, 3 are defects. 3 out of every 500 are defects. Multiply it by the 15,240. So let's go ahead and see what we get there. One 5 2 4 0. All right, so this number here goes to 0.006 times 15,240 is equal to 91.44 defective monitors. Okay, So about 91, 92 defects that we can expect out of that we call it 15,248 population. That's where all of the 500 came out of, okay? So if we say that you guys are a population, we have this Mr. Faye's 5th period class as a population, then I could take 3 of you or 4 of you, and you would be a sample of that larger group. Does that make sense? Okay. Usually in statistics and probability, we don't have information about the population. Okay. If we want to test the effectiveness of a vaccine or a new medical drug, we don't have data on the population. Okay. So what we do is we take a large sample. What we learn about the sample can then be translated to the population. Okay. What we're meaning here is that I don't have the ability to turn on every one of these LCD monitors and run it through a test to make sure it works. So we go through a sample of 500 to tell us about the population of 15,240. Does that kind of make sense? And now as a business person, as this company, you can now say, okay, we're going to have about 90 monitors that are defective, okay, which now we can maybe set up and realize, okay, well, in a month, how do we establish a customer service, a help desk, tech support? How do we, maybe we have to devise a way for us to maybe we know that. Is there something going on with our machinery that is creating that? So if that's unacceptable, if 91 defects is unacceptable, maybe we shut down everything. We go back through our machinery that's putting these things together, or people that are putting these together, and we fix the problem so that we dwindle that 91 down to maybe 60 or something like that. Does that make sense? If you go to P&G has these giant lines that bottles are going through and getting filled, right? Okay. So what they'll do is they'll test every maybe 100th bottle and make sure that it has the same volume. Okay. Because when you go to Myers or you go to Chiefs or Walmart or whatever, and you go to buy Tide, do you want to have to go and kind of lift each one up and see, okay, which one's going to have more volume in it? Which one is heavier, okay? Because the heavier one's going to have more detergent for me, right? Okay? Do you do that? Or you just go grab the first one you see and put in your cart, right? Okay? And their quality control. Now, every one of those on there, every one of those Tide bottles is going to have a different amount in it. But it's not a different amount to where you can determine just by lifting it that it's different. Does that make sense? So they have an accepted margin of error. But if that margin of error gets outside of their acceptance zone, they shut things down and they go and they fix the line, see what's going on, see what the problem is, fix it to get back in that accepted error range. Okay. Probability and statistics, guys, is probably of the mathematics that you do in high school and even in college. Okay. I think it's the most complex and confusing. Okay. At the same time, I think it's the most applicable and useful for everybody as they move on beyond working in high school. Okay, statistics and probability become very, very beneficial in a day to our lives. Okay, we talk about probability. 9 out of 10 dentists recommend a certain toothpaste. Well, what if they only interviewed 10 dentists that all have a link back to Crest? Right? Is that a biased maybe advertisement? Yeah, and they'll always tell you in a commercial in very fine print, 9 out of 10 say this, but we only interviewed 100, or we interviewed 1,000, or they'll tell you how they conducted their survey. But statistics can be very misleading, and people intentionally use them to mislead you. Okay, so that's something we'll talk about throughout the week. No new homework tonight. Make sure that you do start working or finish up that rotations, dilations assignment. But you guys can go to lunch.